Swayam Prabha. Digital India. Educated India.
Now, all these strings that you are seeing here, right, dot text, dot rel text, dot data, and so on, these strings are stored into a separate SHSTR tab, which holds these names of sections, and there is a section called as STR tab, which holds the name of will essentially dump all these strings, okay, which are the section names. Now let's look at the symbol table, which is probably an interesting thing. So symbol table essentially contains the symbol is defining or referencing some location, okay. And one thing which I kind of earlier only told that the symbols that are present in ELF are only symbols that are relevant for linker, and it may not have all the symbols. Okay, so which symbols are relevant for linker? So global symbols. Global here essentially means symbols that are defined in the object file, which can be referenced by other modules, like your normal global variable. Okay, there can be an extern symbol, which is when I do extern int c or something like that. There is local symbol. Now this local, I don't mean the local symbol within a function, but I mean the symbol that is visible only to the current module. So essentially, if you have any variable which is declared as static, okay, and note there is no entry for symbols that live on stack, okay, because those are not needed for linker at all. So this is what a symbol table has. Essentially, it has name, value, size, type, and I'll illustrate this through some examples. So let's take the same program that we had, right? If I dump the symbol table, which I can do using readelf-s, this is what you would see, okay? This is the symbol table corresponding to this object file. So you can see that there is something called as a type, and which is essentially indicating what type of symbol it is. So for example, for any variables that you have declared, the type is object. Okay. Any functions you have declared, the type is func. Okay. So main symbol is of type func. ARR symbol is of type object. Okay. There is something called as size. So which is essentially giving size of the variables or symbols. So init var is of 4 bytes. Okay. ARR is of 12 bytes. And uninit underscore var is of 4 bytes. So it's essentially giving the size which was coming from this. There is something called as value. Okay. Now value is an interesting thing because value is essentially representing offset of that particular symbol. Okay. So you can see that init var is at offset 0. Okay. ARR is at offset 4 because init var is occupying offset 0, 1, 2, 3 because it is of 4 bytes. Then ARR is at offset 4, and since ARR is of 12 bytes, the next variable, which is var1, is at 16th offset. Okay, again, remember these values are in hex, so 10 essentially means 16. And then there is this Y1940. Which is at offset 4 hexadecimal 14, which comes out to be 20. Okay, so you can actually see that the way things are allocated. Okay, so init var was at offset 0, after that ARR, after that var, and after that Y. So if you actually examine, so let's say you start running this program and you print addresses of these variables, you will see them in this order. Okay, not that the value will be 0, but first you will see init var, 4 bytes after that there will be ARR, 12 bytes after that there will be var1, and 4 bytes after that will be Y. Okay.
Why are there two objects at the same address, line 12 and 13?
Line 12 and 13, I'll come to that. Okay. But that's a good question. Okay. So one of the things which I didn't mention so far is what is this offset representing, right? So this offset is essentially within a section. Okay, so there is this field which you can see, which is called as n index, or it stands for SHN index. And you can see that init var has value 3 and main has value 1, ARR has value 3, Y has value 3. What is this representing is this is representing which section does the symbol belong to. Okay. So init var actually belongs to third section, and if you examine the section header, you will see that the third section is data. Okay. Similarly, main is belonging to section 1, which means and it is a .text section. So think of it this way, that every symbol that you have is defined in some section, and which we already saw earlier, right? We already saw the init var, ARR, var1 and Y go into data section, right? And main goes into text section. Okay, and this offset which I mentioned is representing offset within this section. Okay, so wherever is .data section, at offset 0 there is init var, at offset 4 there is var1, and so on. Okay, so that's why it is that way. Okay, and now to answer the earlier question, the reason uninit var is at offset 4 is these two are actually different because they are not belonging into the same section. This belongs into something called as common section. Okay, does that make sense? So the offsets can be same if they are across two different sections, but if we are talking about two objects within the same section, they will not have same objects. They will not have same value or offset unless they are kind of alias to the same location.
Yes, thank you.
Okay. Now, this is what I meant. Uninit var goes into a common section. Now, what is common, etc., I will leave it as an exercise. But if you are interested, search for something called as tentative definitions in C language, which goes into details of what common is and where it comes from and so on. Ideally, this should have been in BSS section, but for a variety of compatibility reasons of C with Fortran, it goes into common section. Okay, printf doesn't has something called as UND, which is essentially indicating that this doesn't belong in any section because it is undefined, because printf is not defined in this program. Okay, printf is defined somewhere else, which is why it doesn't belong in any section and it belongs into an undefined category. Okay, and that's how linker would also know that printf is one of the symbol that somehow needs to come from somewhere else and is not part of this file. Okay, so you can now actually combine both the things that we learned, right? So you remember we had learned we can dump the content of data section using obj dump, right? And we now know which symbol belongs at what offset within that section. So if you actually dump it this way, you will see that association. So you can, if you disassemble the data section and provide this additional flag -j, it actually will print the symbolic references as well. So you can see that the init var has this content, ARR has this content, var1 has this content, and y.1940 has this content. The reason they are in the reverse is because this is a little Indian representation. But these offsets, now you can start corresponding to what the offsets you are seeing in the symbol table.
I had a question.
Yes.
Like for all the other variables like var and ARR, they're named as like int var, init var, and ARR. But for why is it like y.1940?
Correct. That's a good question. And I think I had it as in the subsequent slide. So we'll talk about that there. Okay.
Sure.
Now let's look at the next thing which we didn't see so far, which was a bind field. Okay. So bind is essentially indicating the same thing which I was mentioning earlier, whether it's a global symbol or a local symbol. Global essentially means that the symbol might be used in other object files as well. Local means this symbol is used only in this object file. Okay, so for example, var1 and y.1940 both are marked local because they are static variables. Okay, Remember, I don't know if you know, but one of the things that static variables have is static variables are visible only within that compilation unit. So you cannot, in other source file, you cannot do something like extern int var1, okay? Because var1 is static in this file, okay? Whereas these other global variables that you're declaring, they can be made extern into some other file and they can cross-reference this, which is why all these are global and y and var1 are static, okay? Now coming to the question which someone asked just this, why is the name of this symbol 1940? Any thoughts? Anyone has any idea why it might be this way? Okay, so for example, I have this static int y in function main, right? What if I write one more function foo in this same source file where I again declare something called a static int y, right? I need some way to distinguish between this y which belongs in main and that y which belongs in foo, right? That problem doesn't happen for variables which are declared globally because they are supposed to be unique, right? But for locally scoped variables, there might be name conflicts. So what compiler is simply doing is appending some number, and this logic can change, okay? How this number is calculated can vary from compiler to compiler, but it essentially is simply to mangle the name so that it remains unique within the object file. Okay, to summarize the ELF structure, right? So remember we started off with the ELF header, right? Which had bunch of information about the what type of machine it is, what type of ELF it is, and so on. In addition, it has a section header offset from which you get to the section header, okay? Each of the section header has offsets to various sections where their data starts. It has a size which indicates what is the size of that section. There are some special sections like shstr tab which essentially hold the strings which are used in the ELF. There is a symbol table, okay? Each of the symbol, there is a special symbol again, str tab, which holds the symbol names. Each of the symbol table has a field called as shn index, which is essentially giving the index into the section header, okay, which indicates which section that symbol belongs to. There is a value field of the symbol, which is giving within the section pointed out by shn index, where within that section the symbol starts and what is the size of that section, size of that symbol. Okay. Any questions so far on this?
Yeah, so a section essentially represents, I mean, in the code stream, when the processor executes a jump,
yep,
each section represents essentially a block in which that jump can be made, right?
So typically, I mean, this could vary from implementation to implementation, but if you consider the common x86, Linux, those kind of things, a text section will have the entire code for the program, okay? So when you make a jump from the text section, it will still be within the text section only. So the text section is complete and all the code that you have will belong into the same text section. And I'll show how that happens when linker is dealing with the ELF. Okay, but essentially think of it this way: all the code that you have gets clubbed together inside a single section, and all the jumps that you might be doing will be within that section only.
Sure. So, so the data pointer can jump anywhere else, but the instruction, instruction pointer would be confined to section, the .text
Correct.
section.
Correct. That's the most common implementation. There are exceptions to it, but the most common representation is that way, where all the text section is combined into a single text section.
Sure. Thank you.
I have a question as well.
Yep.
Yeah, during runtime linking and dynamic linking, does the ELF file create extra space to accommodate for incoming data?
So dynamic linking, the way it works is there are various ways by which it actually happens. So there are, I don't want to digress too much for others, but if you are simply linking a library which gets loaded when the program starts, then the process virtual address space already would load that library and you would have that accounted for. For cases where you do a DL open kind of thing, where during the execution you simply arbitrarily open a DL dynamic library, at that point as well, a shared library will be completely loaded if it is not already loaded. But it kind of lives in a separate virtual address space. I mean, it's the part of same address space, but it's separate from the user program where it is loaded. And then there are ways in which the references get resolved.
So are you referring to the input address table, which manages these blocks?
Correct. So the way, if you look at the process memory layout, right? The way it, so your process memory, which is the entire virtual address space, will be divided into multiple segments. So there will be heap, there will be stack, there will be code, right? Now what happens is whenever a shared library is loaded, that gets loaded into its own position where it has a space. Okay, so there is a space where all the shared libraries get loaded, and the way in the memory it will actually might get shared with other processes, the physical storage that is used, but every shared library will get loaded at a unique address space within the address space of the process, and all the references will be resolved in a way that whenever you reference a function or data within that shared library, it will go to that address and actually execute. So dynamic linker will resolve the addresses based on the position where the library is loaded. But the user ELF that is created, there is no, it doesn't expand itself to accommodate the shared library. The shared
Thank you
library
so
will
much.
be loaded at a separate location, but all the references which user code is doing to that will be resolved accordingly.
Thank
Hello.
you.
Yes.
So why keep this separate section header str tab? I mean, section header was already containing the names, the strings.
So the reason we do that is because it keeps the table or the section header structure of fixed size. If you have a string which can be of arbitrary size, then your structure would kind of change, and it will be a variable length record, and that gets, I mean, that makes it harder to index. Now, for example, in the current ELF structure, every section header entry is of the same size and so on. So you can do good pointer arithmetic and move from one section to the next section without having to figure out the string lengths and so on.
Okay. So section header doesn't contain any strings. So it
No,
just contains the
all the
pointers.
strings, yeah, all the strings that are present, be it symbol names or be it section strings,
Okay.
all they are present in separate places, and only indexes of those are stored. Because what happens is string, all of the manipulation that is happening on ELF side, string is not the primary portion of it. It will probably get used only at the first place when linker is trying to resolve things. But beyond that, all the manipulation that happens is completely on non-string stuff. So you don't want strings to be a commonly used data structure because that also slows down linking and
Yes.
related processes.
Makes sense. Yeah.
Okay, moving on, let's try to have a quick quiz. So I have a code, okay, let's say main.c, where I have declared something called as extern void foo. I declare a variable int var1. I call foo and I then print var. I have foo.c where I'm declaring var as extern float, okay? And in foo, I do var equal to 5.0 and I link these together. Any ideas what would happen?
Maybe a runtime error.
Okay, Why do you think it's a runtime error?
Because you're trying to interpret an int as a float.
Okay, so yes, that could, depending on how your architecture is implemented, it might lead to some runtime corruption or error. Anyone thinks this might get detected at link stage as an error? Why shouldn't linker error out, saying that, okay, var is declared as int in main and declared as float in foo? Why didn't linker error out on that? Right? So if you think about it, all the information we saw here in the ELF, nowhere we stored the information about type of variable, right? Did you see anywhere we had that the variable x is of type int or variable x is of type float and so on? We didn't, right? So there is no way linker can check the type mismatch. Okay, and the reason we don't have type information is because languages like C, C++ allows users to create their own types, right? You can have structures, you can have classes, you can have templates and so on. You can create your own types, and there is no easy way for storing all of that information into the object file as a type information for every variable where you can detect this type mismatch. Okay, does that make sense? So the type information is not present. Linker can't complain. You are at your own risk if you write such code. It may just crash at runtime, or it may just reinterpret 5.0 as an integer and print uh, whatever is the representation of FP32 equivalent of 5.0. Okay.
Sorry, I have a confusion. Do we incorporate type information as part of the IR itself, right? So the IR,
IR is there, but IR is at the compiler level, right?
yeah,
Compiler is seeing main.c once, right? And when compiler is compiling main.c, it's not seeing foo.c, right?
yes,
If you write this within the same program, then yes, compiler would detect it, because then it's within, like for example, if here I end up, if I pass it var to something and var is declared as float, and in that function prototype I declare it as int, then compiler would complain because it knows that it is mismatch. Okay, but once you're done generating the object files, right, and compiler would generate one object file for main.c, and then compiler will be separately invoked to generate object file for foo.c. Compiler has no visibility, right? Compiler doesn't know when it sees main.c what is in the foo.c. And when it is seeing foo.c, it has no idea what is in the main.c, right?
sure, sure. And
So
once it
compiler,
compiles,
yeah.
yes, sorry.
So compiler is doing separate compilation. By separate, I mean it's compiling every source file separately. So it cannot figure out if there are inconsistencies like this across source files. I mean, obviously function prototypes, etc., will still be matched, etc., but there is limited visibility of for compiler. Like it cannot really figure out that this var really should have been int because it was declared in main that way. Unless you give this information to the linker, there is no way linker would also know. And as we just saw, linker doesn't have that information, so it can't detect it. Okay. There are
Sure.
some cases where few advanced linking techniques like link time optimizations, etc., may preserve the type information, and linker may actually error out if you're enabling those kind of things. But that's a separate thing. In normal linking, where you're linking to object files, will not give you that behavior. Okay. Let's look at a slightly more interesting example. Okay. So we know that the type information is not present, can't do much, right? Now I have here a different code where instead of type mismatch, here I'm causing a size mismatch, right? So what I'm doing is I have int x, which is 4 bytes, int y, which is 4 bytes. In the other file, I'm declaring x as double, okay? So I'm spoofing the type and I'm linking these two things together. Now what would happen? Any guesses?
Now it should definitely be a sec fault or something.
Yeah, this would be corruption. This is direct corruption.
What kind of corruption?
It can't interpret that data. It just the data can be anything. I mean, yeah, you could read a stream of bits and you could interpret it as an int, but that
Okay.
int would be that int could be arbitrary.
Like when you write 5.0 to x, you're probably overwriting some other data that was placed after x.
Correct. So y may potentially get overwritten, right? Because if you actually examine the ELF for main.c in most common cases, you would see x is at offset 0 and y is at offset 4. And you would likely end up overwriting y. The question I had is why didn't linker error out in this case? Because in this particular case, linker knew that x in main.o is of 4 bytes and x in foo.o is of 8 bytes. And we do store the size information in ELF.
So here linker will extend, change the data type from int to double for x.
Linker doesn't do those kind of things. Linker's job is not to change. Linker's job is to simply, I mean, we'll get into what linker does, but just from a conceptual point of view, linker doesn't get into these kind of complicated stuff. Linker is a simple tool. But I think you can try it out, and if people are interested, you can see why did link. I mean, what few people said that it may end up corrupting data is mostly the correct answer, I would say, where it may end up overwriting y as well. But what I'm more interested in knowing is why didn't linker complain? Because when linker linked main.o and foo.o, it should have been able to say that x in main.o is of 4 bytes, x in foo.o is of 8 bytes. There is definitely some mismatch. I'm not going to link these two things together. There is something phishing happening.
Because of C is a weakly typed language, so you could potentially change the type.
No. I mean, no. Even if you change the type in C, it doesn't allow these kind of type changes.
Where the size is different.
Yes, where the size is different. Because what happens is if you start allowing that, then all of your arithmetic that you may have done on pointers, etc., becomes invalid. So C doesn't allow that. You can change maybe into float. That's also undefined, to be honest, but it would work in most of the compilers. Anyways, I'll leave this as an exercise.
I mean, even if the linker knows, it's not the responsibility of the linker to fix this, right?
I'm not saying about fixing it. I'm saying about detecting it.
Even about complaining about it, because you can have all sorts of memory accesses due to pointers and functors. So,
correct. The question really is more about then why do you even care about compiler giving errors for your logical? Like you might have seen compiler warnings, right? Which say you're trying to typecast a float to int. Is that really what you want to do?
that is because there are memory leaks. Those are like memory leaks and overflows and division by 0. Those are like the most common errors that programmers make.
This is potentially another common error which a naive programmer could make.
So linker only cares about the addresses of things that it links, right? Not about the data types or.
Yeah, I mean, you could argue it that way from a principal's point of view.
Okay.
Okay. I think we are supposed. Yeah, sorry, go ahead.
So the value of x in the main will get overwritten by the x in the foo, right?
Yes, and it would accidentally also end up overwriting y. Because it would, this x equal to 5.0 in foo would write 8 bytes. And that essentially means x gets overwritten and y also gets overwritten. I mean, assuming x and y were allocated in that order, which would happen in most common cases.
Okay,
So
so that
also
means
the linker doesn't know if it's X and Y, like it
Correct.
can
Linker
can
will not
interpret
be
it to be an
correct.
array
Correct.
also, right?
Linker will not be able to detect the fact. Yeah, it could have been array or anything. Yes.
Yeah,
Linker
so
is
like
linker won't detect the overwrites and those kind of things.
so linker don't know the context of the source code, so
Yeah, what I meant originally was linker does know that somehow in foo.o I'm seeing x as 8 and somehow in main.o I'm seeing x as 4. Yeah, the size of x and size of x in foo.o. Okay, anyway, I think there is, so Ramakrishna sir, there is a scheduled break till 4:30, right?
Yes, yes, yes.
So,
We can
so
even take a shorter break, but some break would be preferable. They had a long day and then they have a long night as well.
correct. So we'll stop here and then once at 4:30 we'll start with linkers.